Okay, so I want to continue discussion since last Monday. And so let me just review a little bit the basic concept. Well, when we talk about transmission line, we're dealing with a circuit that is much longer than the radiation wavelength. Therefore, at every different point, the voltage and current are going to be different. So the wave interference and refraction interference, constructive interference, disruptive interference are going to be important. Okay. Therefore, if you want to borrow the concept from the round circuit theory you learned about a long time ago, you have to chop the transmission line into a very small section. Okay. Therefore, the voltage here and here are very close to each other, and you can derive the differential equation to describe the voltage and current relationship over a small differential length delta z. OK， 所以在这一段里头呢，你可以用 round circuit 的 theory 你学过的来在这一小段这个电路里头，你可以用你学过 round circuit theory 来做计算。所以呢，你得到两个式子，这两个式子，可以组成两个 wave equation 出来 for the voltage and current. Okay. And it does know the solution of this equation, so actually you can sort of write down the solution into this form and this form. One telling you that the signal is propagating in the positive z direction, and this term is related to the signal propagating in the backward z direction. Okay, but one thing you have to be careful that this gamma value could be imaginary, could be a real number. And last time I told you and actually write down the derivation for you that the real part of this gamma is responsible for the attenuation of the signal along a passive transmission line. In some cases, if this line is an active element, 你有外加能量进来，它是一个 active 的这个 transmission 一个 material 的话呢，这个 alpha value 可以是它的放大，而不见得永远都是它的 attenuation. Okay, for example, if we send a wave into a piece of laser material. 这个镭射的物质里头呢，这个大陆叫做激光的这个物质里头的话，那你有外加能量，这时候呢，这个阿尔法的值could be positive. Therefore, it tells you that the signal is growing over distance. Okay. So this is one thing you have to pay attention to. Gamma could be a real number, could be an imaginary number, and very often that you have both the real number and imaginary number, depending on the value of R, L, G, C. Okay, and you just cross out R and G. 这是 resistance, 这是 conductance. You get a pure imaginary number. This means that you only have this propagation term. 所以呢，这个 attenuation 来自你的 R 跟 G 的 ohmic loss. Okay, this attenuation constant alpha comes from ohmic loss R and G. So if you have a lossless line, 如果有一条线是没有 loss 的话呢，基本上 you don't have attenuation and therefore you don't have this alpha. Okay, so this is some concept you have to check with you. And this is just a drawing telling you that if you have a lossless transmission line, then you're going to have this kind of ray curve oscillating and propagating along distance without any attenuation. Okay, if alpha is not zero, if you have some finite value of alpha, then the wave is going to attenuate over distance. Okay, any question? No? Then I want to introduce you a concept. Well, this concept is called dispersion. Dispersion 在中文好像叫做色散。OK， dispersion 这个概念是什么呢？也就是说，along a transmission line, you could propagate different frequency components. All right. Sometimes you have single frequency signal, say 100 megahertz. Sometimes you transmit signal with 400 megahertz. 一条线你可能送不同的频率。OK， 像这个ICRT 有一个频率，中广有另外一个频率。OK，and this transmission line behave differently for different frequency signal. And the perhaps the low frequency component propagates slower or faster, or perhaps the high frequency component propagates faster or slow. But the speed, the propagation speed for the two frequency components are going to be different. For this case, we call this transmission line dispersive. OK， 所以 dispersion 的意思就是说，它这个电磁波在这个线里头跑呢，不同频率会跑不同速度，听得懂吗？不同频率的电磁波在这个 transmission line 里头跑的会是不同速度。如果是这样子的话呢，这条线是有 dispersion 的。OK， so last time we already calculated the phase velocity. That is omega over beta, or without any loss. We say this is omega over k. Right? Last time we talked about plane wave, but now you have loss. Your gamma is equal to alpha plus g beta. So this term is the term responsible for propagation. Therefore, now your phase velocity is equal to omega over beta. Alpha is not going to affect the propagation speed of your wave because your wave V or I is going to be written into this form, cosine omega t minus beta z if it's propagating along the plus z direction and then an initial phase. So for this wave, if you set this to be a constant, then you end up having UP, your phase velocity is equal to omega over beta. Okay. Previously, we have an expression that is cosine omega t minus kz plus phi 0. This is a plane wave without attenuation, and we use a symbol of k. Now we use a symbol beta to sort of tell you the difference between a wave with attenuation and a wave without attenuation. OK， 所以呢，这时候你会看到这个式子变改写成 omega over beta. OK， well, if this is a function of frequency, then this means that this transmitting material or transmission line has dispersion. Well, what happens if you have a line with dispersion? 这 dispersion 会造成什么效果？我们来看一下。如果说 if you have a wave containing a lot of frequencies， 如果是只有一个单一的频率的话，你画出来会是怎么样 ？If you have a single frequency 的话，你这个是single frequency wave， right？ 你画出来会是这个样子。It's a perfect sinusoidal wave. But if you put several sinusoidal waves with different frequencies, then you can synthesize this kind of pulse, voltage pulse, current pulse, or electromagnetic pulse. 当你看到一个 finite width 的这个讯号的时候，有特定宽度的话 then this is a signal with a lot of frequencies inside. Okay. 你如果看到一个固定宽度的话，you learn about Fourier transform, right? If this is finite in the spectral domain, it's going to be a broad signal. for example, if in the time domain, if I have sinusoid wave, 每个人都学过 Fourier transform， 在 frequency domain, you're going to have a delta function. F0 is t is going to be 1 over f0. Right? 熟不熟悉？很熟悉吧？没有，傅列分析没学过？有学过吗？这个 sin cosine 的一个式子 Fourier transform 之后，不是给你一个 delta function 吗 ？Fourier transform 基本上就是告诉你这个讯号的频率，对吧？大几的时候学过 Fourier transform？ 大二的时候，现在是大几？大三，所以刚刚学过1年，还记得？还是忘了。Okay. All right. Now, if I have a signal like this in the time domain, let's take a Fourier transform. I don't have phrase. Run it. If I take a Fourier transform in the frequency domain, I'm going to have also some width. This width is called tau 0. This width is going to be 1 over tau 0, roughly. What it means is that if you have a finite pulse width in the time domain, in the frequency domain, it tells you that there's many frequency components inside. Okay, so only what you put a lot of frequency together to get a finite pulse width in the time domain. Okay. 所以呢，当你看到 if you have like a pulse like a signal in your transmission line, this means that there's a lot of frequency component inside. So if you put this pulse into dispersive transmission line, so if you put this into a dispersive transmission line, different frequency component in this signal is going to propagate with different speed, because this line is dispersive. 所以呢，这里头可能，譬如说有蓝的，有红的，蓝的的话频率比较高，红的频率比较低。After some distance, the pulse is going to be spread out. Okay, and it turns out that the pulse width at the end is going to be longer than the pulse width at the beginning. 这不太好，为什么？ Because if you transmit a digital signal, this is one, then you have several pulses like this to start with. But in the end, you can spread out like this. These two signal pulses could be overlapped with each other because the pulse is spreading due to the dispersion of the transmission line. OK， 听得懂吗？你如果有一个 transmission line， 它是这个里头讯号跑的速度跟频率有关的话呢，你放一个这个脉冲讯号进去 ，after some distance, the signal could be spreaded like this, and then you have overlapping between your signals. Okay. So very often that you try to remove the dispersion from your transmission line. So let's take a look. How to remove this this dispersion. Before we do that, let me define one very important parameter. It's called characteristic impedance. This characteristic impedance is defined to be the ratio of the voltage signal over the current signal in one propagation direction, along the positive propagation direction. If you want to define the ratio according to the backward propagating signal, then you have to put a minus sign in the expression. Okay. How would you do this? How would you find out the expression for the characteristic impedance? Well, we have one expression before. Let's just pick up, say, this expression. Okay, and your VZ has taken to be V plus exponential plus gamma z. Okay, and your I for the forward propagating signal, you have I naught plus exponential plus gamma z. And then you put these two expressions into this equation. Okay, 你把它放到这个式子里头来，或者放到这个式子里头来。And then you can find out the ratio of this over this. You're going to get this expression. And let's define this to be a characteristic impedance Z0. Okay, 这是你计算的方法。你知道它的解长得像这个样子，你就把正的或把这负的也把它抓出来，放到刚刚那个式子里头来。And you end up having this ratio equal to gamma over G plus J omega C, or R plus J omega L over gamma. OK， 很简单的一个代数的计算，一个微分的计算。So when I show you this solution, you tell me how many variables inside. 这里头有几个不知道的这个参数变数。这里头 gamma 的话是你知道的东西 because RLGC is something intrinsic to a transmission line. You can measure the inductance, capacitance, resistance, conductance associated with the transmission line. So this gamma is known to you. 你知道的 ，OK。所以这个里头，这两个式子里头有几个你不知道的变数。除了 gamma 之外，你知道这个是什么吗？你知道这个是什么吗？不知道。你知道这个是什么吗？不知道。你也不知道这个是什么，所以你不知道的有几个？4个 ，fine， good。但是你有了这个关系之后 ，this is known to you. Once you have this, you reduce the 4 variables into 2. Right? 譬如说，你如果知道这个，那你这个就可以求出来，因为这两个你是知道的。OK, any question? 你如果知道这个，你可以求出这个，因为这两个你知道了。So initially you have 4 variables, but once you define or calculated this characteristic impedance, you reduce the 4 unknown variables into 2. 所以这个解答不是那么的可怕了 ，right? Initially you have 4 unknown variables, now you only have 2, and later on. We're going to solve the 2 unknown variables according to the boundary conditions. If you look at this transmission line, there's a boundary here will give you a solution for 1 variable, and then you have an additional boundary conditions right here. Will give you the final solution. 所以这样了解吗？你刚开始的时候呢，有4个不知道的这个变数，但是并不是那么可怕。Okay, once you define this, you reduce 4 unknown variables into 2, and then later on we're going to add 2 boundary conditions into the circuit, and then you can solve all the variables. Okay, let's try to understand the transmission line in some special cases. Well, the first special case is that if we have a lossless line, suppose that your transmission line is lossless, and in fact, you really want to build a transmission line with small, very small loss, because you want to use the energy for doing something else, right? For doing some your applications. And suppose that you have a lossless line. This means that your resistance and conductance are 0. Then, according to this equation, if R and G are 0, then you only have propagation term. Your attenuation is 0. So beta is very easy to be calculated. Just take out R and G, then your beta is equal to omega multiplied with LC, square root of LC. Okay, so this is the simplest case. And the phase velocity can be calculated, which is 1 over square root of LC, and ideally LC are independent of frequency. 它跟频率无关，所以我们说这是一个这是一个 transmission line without dispersion. Yeah, transmission line 没有 dispersion 是什么意思？帅哥告诉我一下。啊？同一个频率怎么样？啊？不是啊，这个一个频率的波是你自己放进去的啊。哦。你要放一个频率就放一个频率，你要放两个频率就放两个频率啊。但是不同频率的这个波在里头跑的话，它有什么现象？没有 dispersion， 这里没有 dispersion。所以不同频率的波在这个 transmission line 里头跑，会有什么特性？这不同频率的波，通通跑的一样速度，是不是？对啊。对呀、so easy, right? 所以你如果有个 transmission line without dispersion, this means that if you put a lot of frequency components into this transmission line, all the frequency components are going to propagate at the same speed. So what happens is that if this is a transmission line without dispersion, the pulse width will be preserved. The pulse width of your signal will be preserved during the propagation inside this transmission line. Okay, 它不会跑了一段之后，它不会变成这个样子。它在这条线里头跑呢，就是维持那么大的这个 pulse width. If you don't have dispersion, so this is a quite nice result. In fact, you really want to have if you can make a lossless line. But in fact, it's going to be hard to fabricate a transmission line without any loss, unless you use a superconducting material. The superconducting material is very expensive. At the same time, it has to be operated under low temperature. Okay, so usually you have some loss. Okay, so usually you have some loss. Suppose that your loss is quite small compared with the inductance and capacitance. Then you can do Taylor expansion to gamma. 你可以做一个这个 Taylor expansion. 然后呢，因为这个比这个远小于这个，所以呢，你把这个从根号拿出来之后呢，你可以做一个这个Taylor展开式。With Taylor expansion, you can calculate some finite attenuation constant because this is typically if you just use a copper as your transmission line, there's always some small loss over some distance. Okay. And so after doing this Taylor expansion, you can calculate some attenuation constant. And then you can also calculate the beta, the propagation constant, and deduce the phase velocity. For low loss line, this phase velocity is very close to 1 over root of LC. Right? It's more or less dispersionless, but in fact, there's still some dispersion, high order dispersion in this expression. Okay, it's not completely dispersionless. Look at this approximation right here. Okay, 这里有一个这个近视在这个地方。那 characteristic impedance 也是很重要。 将来你如果要算它的这个讯号的反射的话，you have to take into account this characteristic impedance all the time. Okay. So for lossless line, you cross out R and G, and apparently your characteristic impedance is going to be equal to square root of L over C. Okay. 那这个同样的，你可以用它的展开式替你这个 lossless line 做一个这个 characteristic impedance 的计算。OK， 保留到第一个first order term。Well, there's a special case that you can actually have some loss in the line, and sometimes you could have a dispersionless transmission line. OK， 假如你能够设计你的 transmission line R over L equal to G over C， well， 有这么一个 ratio 的关系的话 ，you can deduce that well you have loss in this line according to this expression, but your phase velocity is independent of the frequency. Okay, but this will require careful design of LC and R and G. Okay. 那我们再回顾一下 transmission line 长什么样子。Transmission line 呢 ，one case is that there is a coaxial cable that you saw quite often, and another case is that for high power operation, the transmission line just a pipe. 那这里头呢，我们学静电静磁之后呢，会教你怎么去算里头的这个 RLGC，OK， 譬如说这个导线里头就有 R， 这个导线跟这个导线之间有 G， 那跟这个物质有关系。And for C capacitance， 这个导线跟这个导线之间有电容，可以算得出来。那 L 呢是这个导线里头它会产生磁场，所以有 inductance，OK。So I don't want to just throw you a lot of variables, but I want to bring you to this picture to tell you that in fact RLGC are related to the physical structure of the transmission line. As long as you know the physical structure of the transmission line, RLGC can be calculated. Okay. 有没有问题？没问题，那很清楚哦。各位帅哥有个眯眯眼。眼睛可以张得开吗？不容易张得开哈，早上太早了。好，所以有3个 special case 告诉你了，但是重点在于就是 if you can design something that is dispersionless, that is going to be a preferred design. 那是一个比较好的设计。你如果能够设计出 dispersionless 的线的话，因为讯号传输进去的话，这讯号的脉冲的样子呢不会改变。那它里头的物理的话，基本上是告诉你说 ，different frequency component are going to propagate with the same speed, so you don't have pulse spreading. OK， 这个我们助教明雄最清楚的，因为他随时都在弄这个 laser pulse， 把它拉长，把它压回来，这样，所以 dispersion 对他来说是最清楚的，有问题可以请教他。然后呢，一刚开始的时候我就告诉你。这个 transmission line 是波在里头跑，那 the dimension of this transmission line is going to be much larger than the wavelength. Therefore, interference is important. Interference basically is a concept of at least 2 waves overlap with each other. OK， 你只有2个波放在叠加在一块的时候才会产生干涉。那对一个 transmission line 来讲的话，the interference comes from the refraction of the wave. Okay, so think about this. If you put some load at the end of the transmission line, this could be an antenna, for example. Okay, then possibly when the wave is instant on this location, then there could be some reflection back. So we want to know how much the signal is reflected back, or how could we design a circuit that allows all the power transmitted to your load without being reflected back? OK， 在这里呢，我们就把这个原来式子抓出来。原来的式子呢，这个右手边在这里，你的这个 total voltage across this law is equal to V, the phase of VL. And for the current, there's a total current going through this node, denoted by, the phase is denoted by IL hat. 没问题来，然后呢，在这点上头，你有往前走的波，有往后走的波，所以呢，你有 V naught plus V naught minus. The same thing, you write down the same expression of I naught plus I naught minus. 那在这个设计里头，这个 z 等于0的点在哪里？在这里。Okay, let's denote the origin of z at this location. 所以呢，这个 if I go back to the solution right here, basically I'm setting z equal to 0 in that expression. Okay, you just put z equal to 0 into this expression, then you end up having V naught plus V naught minus equal to VL phasor. Right? Now, again, you put z equal to 0 into this expression, then you have I naught plus I naught minus equal to V equal to IL phasor. But according to the round circuit theory, because you just look at the circuit at one single point, so you can use the round circuit theory to relate VL phasor and IL phasor equal to your low impedance. Okay. 但是呢，你又把这个 V0 正跟 I0 正，透过 characteristic impedance 把它给关联在一块，所以 you can write down I naught plus Z naught equal to V naught plus, right? And the minus I naught minus Z0 equal to V naught minus. So in fact, you can replace this symbol with V naught plus. Replace with this backward current with V naught minus. Okay, then immediately you can come up with this expression. You can come up with this expression. Okay, 好，在这个式子里头，你有两个变数 V0 正V0 负，然后呢，你这个还有一个 low impedance and low voltage right here， 所以这两个式子里头有三个变数 ，right？ 有三个不知道的东西，一个是 V0 正 V0 负，一个是 VL phasor， 这个 ZL Z naught 这些的 characteristic impedance and low impedance are something designed by you, so you know what these values are. 你知道这些值。两个式子有三个变数，这表示两个式子你只能解出两个变数出来。但这里头有三个变数，所以这里头这两个式子呢，告诉你说，你剩下最后只剩下一个不知道的东西。有了这个边界条件之后 ，once you have this boundary condition, you reduce the unknown variables to just one. Okay, so initially we have 4 unknown variables. Now you reduce to 4 unknown variables to just one. The first reduction is due to the derivation of the characteristic impedance. You reduce 4 unknown variables into 2. Now you are further reducing the unknown variables just one because you apply a boundary condition right here. Okay, and later on we're going to apply one more boundary condition at the beginning related to the generator, and then finally you can solve all the unknown variables. OK， 所以从这里的话呢，你就可以算出一个东西出来，这个东西叫做 reflection coefficient。这两个式子，两个联立方程式，你可以算出这个 ratio 出来 ，but you cannot calculate specifically 这个值或这个值，因为里头还有一个变数在里头。Okay, so we define this coefficient to be reflection coefficient, but this is defined under the voltage, not by the current. 好，在这里的话呢，我要另外强调一件事情，就是你看哈，这个low impedance， 你在计算的时候呢，是所有的电压除以所有的电流，所有的电压除以所有的电流 ，OK， 这两个的 ratio， 所以呢 ，it contains the forward signal and backward signal， but when we define the characteristic impedance。 Okay, when we define this characteristic impedance, be careful that the definition is just voltage over current along one direction only. 这个是你要小心区别出来的。OK， 所以这个概念上不太一样。OK， 这个 Z 零这个是只有在一个方向上头的电压跟电流的比例。但是呢，这个 low impedance according to the Raum circuit theory, is the total voltage over the total current at this location. Okay, and so from these two expressions, you can solve a ratio that is the refracted voltage over the forward voltage. 这告诉你说，比如说you come up with 1%, for example, right? It means that the 1% of the voltage is refracted back. 1%的这个电压反射回来，或3%或者20%或100%，说不定。Okay. But this ratio in terms of current, you have to add a minus sign here. And be careful that this is not the energy ratio. 这并不是它的 energy ratio， 是它的 voltage ratio。所以呢，这个有可能是负的值，这个有可能是负的值。OK。那能量的话呢，你会把这个做平方的动作。我们上面介绍过，任何的波，它的 amplitude 的平方 is proportional to the energy. Okay, so this gamma could be positive, could be negative. It's just a ratio of the refracted signal over the full propagating signal, and this amplitude could be positive, could be negative. Okay, therefore, there's in general this is a complex number given by this expression. This is the low impedance minus characteristic impedance over low impedance plus characteristic impedance. And you know that this is in general, this is a complex number. 它是一个复数的值。So you can express this gamma into a polar form, giving the magnitude of it multiplied with a complex exponential. In general, 它是一个复数的值，所以它有相位的。这个反射的这个系数它有相位，可以是负的，可以是正的。Okay, so this is the reflection coefficient telling you how much your signal is reflected back from the transmission line. And of course, you want to minimize this ratio. Okay. Sometimes you are also interested in the signal transmitted into your load, and again, if you take the ratio of the low voltage over the full propagation signal, then you end up having an expression telling you the percentage of the voltage transmitted into your load, say an antenna. Okay, and then you can deduce the efficiency of your energy propagation, energy delivery. Okay, 了解吗？ 这个反射系数跟穿透系数的话很重要，因为它告诉你能量是穿过，是不是送到你要送的地方去了 ，OK， 还有你的能量效率送到一个地方去。Any question？ 没问题，太简单了。
为什么是除以那个 V 零正什么意思
？V 零正是它这个往前方跑的电压的讯号。你可以想象说，你刚开始的时候，你丢一个 V 零正进来 ，OK， 然后呢，到稳态的时候，你有多少这个 V 零负往回走？
一开始丢的话只有 V 零正。
没有，对。那这在稳态的状况之下 ，OK， 稳态的状况之下，你丢了这个讯号过去，然后呢，回来这么多。
那为什么一开始不是有个解是那个 V 零正加上 V 零负？那个是什么意思？
那是一个通解，在这个 transmission line 里头一个通解。
那你那个 VL 是指
？VL 是指这里的最后的稳态的电压。比如说，在一个天线上头，你送出去讯号，这上头最后能产生一个电压在这上头。
那我就问你，那个 Z0 到底是指什么东西吗
？Z0 它的定义的话，就是V 零正除以 I 零正，是一个特性的阻抗。
所以也是等开之后才可以求出来。
No， 这个是你 transmission line 做好了之后，你只要知道 V 零正，你就知道 I 零正。因为这个是只跟这个 transmission line 的特性有关。OK， 那它跟这个后头的接任何东西都无关。你 transmission line 做好了之后，它的特性阻抗就已经固定了。所以上回我拿了一个那个 transmission line 比较粗的那个的 characteristic impedance 就是50欧姆。OK， 所以你拿一条线过来。然后呢，你看它的这个规格，它就告诉你说这条线是50欧姆还是75欧姆之类的。OK， 然后呢，你给它一个 V 零正，那你在上头的 I 零正也就晓得了。OK， and if you pursue if you work on optics, in fact, this expression is very similar to the refracting coefficient of light wave. If I just send a laser, for example, onto this surface, and then I get some reflection back, and this characteristic impedance, low impedance, basically is just the refractive index of the material, 折射率 ，OK。所以任何东西其实能量传输都跟transmission line 有关系，它的这个分析特性有关系。Well, important thing after this point is that now you know how to calculate the refraction coefficient of a transmission line given a low impedance right here. Okay, and of course you know the characteristic impedance of your transmission line that you can calculate. And quite often that we don't pay too much attention to transmission coefficient. Okay, because if you know the refraction of the power, then you can know the due to conservation of energy, you can know the power delivered to this load. So, for example, if I have like a 10% refraction, this means that the 90% energy is delivered to this load if this line is lossless. Okay, so we pay a lot of attention to reflection coefficient, but not quite to the transmission coefficient, because energy conservation will allow you to deduce this. Okay. Now, I want to tell you the standing wave ratio. Now that you have reflection, you want to know how much energy is reflected back. If you have partial reflection, then it's not going to be a complete standing wave because the refracted amplitude is going to be smaller than the transmitted amplitude. Okay, so now you put the reflection coefficient into your expression. Previously you have you have V that is equal to this is all phasor. Minus G beta Z, assume alpha is equal to 0 plus B minus exponential plus G beta Z. Now, you know the V naught minus over V naught plus is equal to gamma. So you can replace this variable with gamma and V naught plus. Okay, so just replace this, write it into gamma multiplied with V naught plus, and then write this into a polar form. Then immediately you end up having this expression, and then you can do the same thing for the current. You have this expression. Okay. I told you that once you put the boundary condition for the rho, you only have one variable, one unknown, that is V naught plus. 所以原来4个这个不知道的东西，现在呢，你只剩一个 V 0正不知道。为什么？因为 I 0正呢，你可以把它写成是 V 0正除以 characteristic impedance Z 0。Okay. Okay, if you look at this expression, it tells you that there's a forward propagating wave, and then there's a backward propagating wave, and the superposition of these two waves give you this expression. And when you have a theta gamma plus 2 beta z equal to integer multiple of 2 pi, 你得到最大的值。如果说这是2派0或2派的整数倍的话呢，你这个电压是最大的。如果说if you have 3派、1派、3派、5派，这里变成负的，你得到这个的最小值。So at different location z, you find maximum voltage or minimum voltage. Okay, you have maximum voltage and minimum voltage according to the value of this theta gamma plus 2 beta z, and z is a variable, beta is a constant, theta gamma is a constant. 所以这代表说，这里头在变的是什么？是 z 而已，在这个 z 不同位置，你有这种大大小小的这个值出来。So the first condition is that if you have theta gamma plus 2 beta z equal to multiple integer of 2 pi, and we put a minus sign here because we define z equal to 0 at this point. 所以这边呢 z 都是负的值。Okay, you have to get used to this minus sign right here because z equal to 0 is right here, and then this is the minus z. So if you have this relationship, then you have a maximum value of the voltage. And if you check this expression for the current, it corresponds to a minimum value of the current. Okay? 所以当你的这个电压是最大值的时候呢，你的电流是最小值。当你的电压是最小值的时候，你电流是最大值。OK， 这是这个驻波干涉的结果。Okay, the same thing, you can also check the point where you have minimum voltage and maximum current corresponding to this value equal to R integer multiple of pi, but put the minus sign here because you have minus z in this direction. Okay, so this is sort of the pattern, the entity pattern associated with the refracted wave on a transmission line. And so this is sort of incomplete standing wave. If it's a complete standing wave, then you have a 0 point right here. As in general, your refraction coefficient is not going to be equal to 1. 所以呢，只有 partial refraction 的话呢，你最低点不会降到0。